Hello students, in this lecture I'm going to teach you that in the control of electrical machines section, that is a solid state control of DC drives using full wave control converter. So as you can see in this diagram, it is the full wave control rectifier, the control converter comprising of the four thyristors T1, T2, T3 and T4. It's fed from an AC supply, and this is the RLE load depicting a DC motor. That is, a DC motor can be represented by a RLE load. Now first of all, we will see what is a waveform that we get in this circuit at the output branch. That is what is my output voltage, that is V0, and what is my output current, that is I0. So here we see that this is the V0 average, that is the output voltage what we get in this form. This is the firing angle alpha, and this alpha can vary from 0 to pi, that is 180 degree, right? Now so as we vary the alpha, the waveform will keep changing, but here we have shown the waveform for a particular value of alpha. Let's say alpha is equal to 30 degree or anything, alpha is equal to 35 degree, anything. So for this value of alpha, we get a waveform of output voltage like this. This is very waveform is understandable in this part of the waveform. Actually, in this part of the waveform, that is alpha 2 pi, this region, it is T1 and T2 conducts, that is T1 and T2 conducts, and this part of the region, it's still T1 and T2 conducts, although the voltage has become negative, but T1 and T2 will continue to conduct because of the high value of the inductance at the output, because of this high value of inductance at this output. So here T1, T2 continues to conduct beyond pi. This is very important feature of this circuit. Normally T1, T2 should stop conducting at the value of pi if the load was resistive, but as the load here is inductive load, so the high value of inductance at the output circuit results in the voltage being negative, right? And T1, T2 conducting even beyond pi. So again here it will be T3, T4 from pi plus alpha to 2 pi plus alpha, that is T3, T4 and so on. This is also T3 and T4, right? So now from this waveform, and this is the output current waveform. Here we have considered the current to be a constant current output, although this is only possible in case of a continuous conduction mode. Continuous conduction mode refers to, you can see that the output current does not become zero anywhere. At any instant it does not become zero. It continues to remain a constant value throughout. But this is not the case always. Sometimes it may be that the current falls to zero value. In that case the mode becomes discontinuous conduction mode, but here it's continuous conduction mode as we have considered. And we have also considered the output current to be constant, and this is only possible if the output circuit has a very high value of inductance. This is only possible, again I'm telling, the output current is constant. This is only possible if the output circuit has a very high value of inductance. Now from the waveform we can calculate the output average voltage. This is the formula for the average voltage. It's very understandable. Here I have shown that the alpha may vary from 0 to 180 degree. So the output voltage 1 by pi alpha to pi plus alpha Vm sin omega t d omega t. So this, after calculations, it becomes 2 Vm by pi cos alpha. It's a very known result. You must have heard it before also in the power electronics course in your third year or fifth semester classes. So this output voltage becomes 2 Vm by pi cos alpha. Now from this output voltage we can see this output voltage can vary from positive to negative. For 0 to alpha, from means with alpha varying from 0 to 90 degree, this value, this V0 remains positive. For alpha from 90 to 180 degree, this V0 becomes negative. That is, there may be a possibility in this circuit for change in this polarity of this voltage. When for alpha greater than 90, that is 90 to 180, this polarity of the voltage, for supposing we have considered the reference polarity to be plus minus, for alpha 90 to 180 degree, this polarity will change, that this will become plus and this will become minus, right? So with the V0, so therefore in the V0 I0 plot we can see that with full wave converter, because this V0 changes polarity with the value of alpha that is greater than 90 degree, this in this V0 I0 plot there is possible two quadrant operation. I0 cannot be negative, it cannot be negative, because I0 always will follow this direction, that is from top to bottom, because these are unidirectional devices, this thyristors, it will always conduct from top to bottom and they will always come like this. This I0 cannot change direction. What can change direction is this V0 with the variation of alpha. So this, with the variation of alpha, this two quadrant operation is possible, one in the positive V0, negative V0, and this negative V0 is for 90 less than alpha less than is equals to 180 degree, and this positive V0 is for 0 less than alpha less than is equals to, rather 0 equal to less than alpha less than 90 degree. So now using full wave converter we get two quadrant operation. In the first quadrant, power is fed from the AC supply to the DC load, that is, while operating in this quadrant the power is fed from the AC supply towards the DC load, right? AC supply to the DC load motor, that is the motor side. While in the fourth quadrant operation, that is in this quadrant, power is fed from the DC side to the AC side, that is DC power to AC power it is converted into, and the converter acts as a line commutated inverter. What is the function of the inverter? The inverter basically converts the DC power into AC power. So for alpha varying from 90 to 180 degree, it just acts as an inverter, but it's line commutated inverter. Okay, so now from the circuit itself it is very much understandable that it is that the back EMF, or this E, what we see it, E is equals to V0 minus I0 into R. The L does not come into the picture because we are dealing with average values here, and the average value of L and the average voltage drop across L is always 0. That is why the L does not come into picture in this equation. Again, we know that from the DC machines chapter we have studied that the back EMF is given is proportional to flux and the speed. K is a constant, speed constant. Now for a separately excited motor we know, or shunt motor, phi remains normally basically constant, so we can equate. So putting the value of E here, K phi omega n is equal to V0 minus I0 R. From here we get omega n is equal to V0 by K phi minus I0 R by K phi. So for I0 is equal to 0. If there is no load, if the motor is running at no load, so I0 becomes 0. So in that case V0 by K phi becomes a no load speed. So with as you load it, with increase in the loading, as I0 increases, this omega starts decreasing. But we are interested in not in speed versus current characteristic, we are interested in speed versus torque characteristic. So therefore we have to replace this I0 in the form of torque. So from the torque relation we know that the torque is equals to K phi Ia. Here Ia basically refers to I0, because this is the armature circuit that you have drawn here. So this current entering the armature is I0, which we normally represent as Ia. So torque is equals to, see here Ia is equals to I0, so I0 is equals to Te by K phi. So if I0 is equals to Te by K phi, so omega n here can be written by V0 by K phi minus, in place of I0 we put Te by K phi, so Te into R by K phi square. So in that case V0 we know 2Vm by cos phi, as we have derived it from the waveforms, and we just put the value of this value of V0 in place of V0 here, and we get this equation 2. So from this equation we see that it's a straight line equation. It's a straight line equation with r by k phi square, the slope of the equation, and it varies with alpha. As you vary alpha, this omega n will vary, and torque is a independent variable while omega is a dependent variable. As you vary the torque with a particular value of alpha, as you vary the torque, the omega will vary with a different slope, omega n. So this is we are nearing the end. So this is the torque versus speed or rather speed versus torque characteristics. We see that for alpha is equal to 0, as cos alpha is the maximum 1. So this plot is for alpha is equal to 0 with variation of t, we get this plot of omega n. For you put alpha is equal to 30 and vary the torque, the omega n will vary like this. For alpha is equal to 60 will vary. And now the interesting thing to see that for alpha is equal to 90 degree. For alpha is equal to 90 degree, it will start from 0, as because for t is equal to 0, there is a no load t is equal to 0, so this term becomes 0, and this v0, that is 2Vm by pi k phi into cos alpha, for if you put alpha is equal to 90 degrees, so this term also becomes 0. So for t is equal to 0, this omega n becomes 0. So it starts from 0, and gradually as the torque is increased, it becomes negative. With further increase in alpha beyond 90 degree, that is from 90 to 180 degree, the plots will continue to become like this. That is, the plots will be parallel to each other, but the point at which it cuts the speed axis, it will change. So this is basically the motoring region. There is a motoring region for alpha greater than 0 to 90 degree. That is the first quadrant operation. And the fourth quadrant operation, this region, actually it's not the motoring region. This gives here the power is fed back from the DC side, that is the load, that is the DC load, to the AC supply. That is DC to AC power conversion is taking. So basically here what happens, it's not motoring action takes place, it is actually reverse regenerative braking. Why regenerative braking? We know what is regenerative braking. In case of regenerative braking, the power is not wasted. There is a power from the load side is fed back to the AC supply. Right, here also the same case, that is the DC power from the load side is fed back to the AC supply. So there the power is not wasted in this case. That is why it's reverse regenerative braking. So it is operating in these two quadrants. It's not possible. So if this converter was not a full wave control converter, if it was in a half wave control converter, this operation, there is a two quadrant operation, would not have been possible. So this is the main feature of the full wave converter. Control of DC motor drives, that is two quadrant operation is possible, right? So I've sent you the PDFs for this lesson, and I've given you these videos. See this video in my channel, Electrical for You. If you have any problem, ask me in the WhatsApp group.